Thanks for watching, and here is how to solve a system of ODEs the cool way. Because consider the following coupled system with initial condition. In order to decouple it, we would like to use the Laplace transform, which is defined the following way, although we won't use a definition. And more importantly, what it does, it transforms differentiation into multiplication. In fact, we have the following property. The Laplace transform of the derivative is just the product of s and the function minus the initial value. And in particular, because of this property, it works very nicely with differential equations. And in fact, what we would like to do is apply the Laplace transform to each equation separately. So, beautiful L of x prime equals 7. Beautiful L of x minus 3. Beautiful L of y. And same thing for the second equation. And again, what's amazing here is those two left-hand sides simplify tremendously, because what we get now is that s, Laplace transform of x, minus the initial value of x, which was 7, equals 7 Laplace transform of x minus 3 Laplace transform of y. And similarly for y, so SL of y minus the initial value equals 12 is 10 L of x minus 4 L of y. And again, the miracle is, in the second equation, there is no differentiation whatsoever. And in fact, what this becomes is simply an algebraic equation with L of x and L of y that we'll be able to solve fairly straightforwardly. So what we get is in fact a linear system with L of x and L of y after rearranging some of those terms. And the way we can solve it in this case is simply by using Cramer's rule. So for the denominator, you just take the determinant of this matrix, which looks scary, but is not that bad after all. So s minus 7 times s plus 4 minus 3 times minus 10, which then becomes s squared minus 7s plus 4s minus 28 plus 30, which ends up becoming s squared minus 3s plus 2, which can be conveniently factored into s minus 1 times s minus 2. So that will be our denominator for L of x and L of y. And now, to calculate L of x, you take the ratio of, well, this thing and the determinant, but where we replace the first column by 7, 12. And so in the end, we get the following. Again, the ratio of two determinants. First, where you replace the first column and the denominator that we found, which in this case becomes 7s plus 4 minus 3 times 12, so minus 36 over that gibberish. And that becomes 7s plus 28 minus 36. 28 minus 36, I believe that's minus 8. So yes, 7s minus 8 over s minus 1 times s minus 2. And as is usual for Laplace transforms, what we would like to do is a partial fraction decomposition. So you write this as a over s minus 1 plus b over s minus 2. And I will skip the algebra, but in that case, turns out you get 1 over s minus 1 plus 6 over s minus 2. And here comes the great reveal. So those two things are precisely Laplace transforms of functions. Namely, it's the Laplace transform of e to the t, like et wants to go home, plus 6 e to the 2t. So what do we get? The Laplace transform of x is the Laplace transform of e to the t plus 6e to the 2t. And because Laplace transforms are one-to-one, we eventually get that x of t, the function that we want, is precisely e to the t plus 6 e to the 2t. Wow, look how direct this is. We directly got our function x of t. And similarly, if you replace the second column, you can get y of t. So here's the work in case you're interested. So in this case, magic, we replace the second column by 7, 12. You do the determinant, you get 12 times s minus 7 plus 70. And you simplify this to 12s minus 14. You do another partial fraction decomposition to get 2 over s minus 1 plus 10 over s minus 2. And once again, we have the great reveal. This becomes Laplace transform of 2e to the t plus 10 e to the 2t. And therefore, our second mystery function y is 2e to the t plus 10 e to the 2t. And therefore, combining this with our result for x, we get the following. Our solution to our system of ODEs is simply e to the t plus 6e to the 2t and 2e to the t plus 10e to the 2t. Or if you'd like, in vector form, this becomes e to the t times 1, 2 plus e to the 2t times 6, 10. And this is how you can solve a system of ODEs using Laplace transforms. And of course, you may say, well, why not just use eigenvalues and eigenvectors? Of course you can do it. But what I like about this, it's a little bit more direct. It doesn't use any abstraction whatsoever. And not only that, just like for usual Laplace transforms, what's great is that you can solve inhomogeneous ODEs using that way, where you have an f term on the right, without using variation of parameters or undetermined coefficients. And you can moreover solve systems where you have jumps or convolution or Dirac delta distributions. How cool is that? All right, if you like this and want to see more math, please make sure to subscribe to my channel. Thank you very much.